Welcome to this quantum seminar after a long hiatus. So today our speaker is Yichen Huang. So I'm very happy to have Yichen here. He's actually my classmate in undergrad. So Yichen got his PhD in UC Berkeley under the supervision of Professor Joe Moore. Then he moved on to become a postdoc at Caltech, and currently he's a postdoctoral fellow and he's been in the Boston area for a while, and currently he's at Harvard. So Yichen, in terms of the research area, Yichen has been working at the intersection of condensed matter physics and quantum information. He was able to rigorously prove many interesting statements using quantum information technique, statement about related to quantum antibody systems. So Yichen, today he will tell us about quantum entropy thermalization. So Yichen, please take it away.
Thanks for the organizers for giving me the opportunity to present at Cornell. And this is my first time to present my research at Cornell. And today I will be talking about quantum entropy thermalization. That is the thermalization of the von Neumann entropy in quantum many-body systems. And this is a joint work with Aaron Harrell from MIT, and he was my advisor while I was the postdoc at MIT. And these are the references for the talk. These are references for the talk today. So before I talk about entropy thermalization, let me first say a little bit about thermalization. So thermalization is something that is what we frequently see in ordinary life. For instance, from the figure, you can see that the milk and the coffee is thermalized. And in this talk, we will focus on thermalization in quantum systems. And this corresponds to the statement that the state represented by the density matrix at time t converges to or approaches the Gibbs state E2 minus beta h over the partition function. And this is a statement about thermalization. And in this talk, we will focus on an isolated quantum many-body system. And in such a system, the dynamics is unitary, so that if initially we have a pure state, that is, if the system is initialized in a pure state, then the unitary dynamics always gives you a pure state at any time, so that it doesn't approach to E2 minus beta h. So in order to observe thermalization, we need to we divide system into two parts, and I call it A and A bar, or a complement of A, so that we might view that A bar is a bus of A, and then ask a question of whether the reduced density matrix on subsystem A thermalized. So that because we divide system into a subsystem and its complement, and view its complement as a bus, we require that the size of A is less than or equal to half of the total system size. But we do not require that A is much smaller than A bar, as long as it is less than or equal to the size of A bar. And thermalization means that we have a thermal state E2 minus beta h. So this is a very general statement. And in particular, we, as I said, we observe thermalization. This is a phenomenon that occurs frequently. And in order to understand it, we need to have some explanations of how the deep state E2 minus beta h emerges. And there are some very standard arguments. For instance, arguments based on a so-called ergodic hypothesis, or the principle of equal prior probabilities. And these are standard arguments in statistical mechanics, and it is, in some sense, already taught in introductory statistical mechanics courses, so that I do not explain it in depth here. So roughly speaking, these arguments are kind of very general in the sense that these arguments do not rely on the microscopic details of your system. And in this sense, they are universal. But this being universal is a good point, but it is also, in some other sense, a bad point, because if, let's say, give you a particular system, it is difficult to verify whether this hypothesis or this assumption is valid or not for your system. And if it is not valid, then it is also difficult to disprove this hypothesis. And in particular, we know that the thermalization is a very tricky statement because not all systems thermalize. So it is important to understand that is beyond this, without using this hypothesis. For instance, whether we can derive thermalization directly from the more fundamental laws of nature, in particular, whether we can derive E2 minus beta h just from axioms of quantum mechanics without adding additional assumption. And this is a question that we would like to address today. And in this talk, we will particularly address entropy thermalization. So in this slide, I will just give some motivation of why this is, what is the statement, that is, what is a statement of entropy thermalization and why this statement is expected, is generally expected to be true. So the central point, central object here is the so-called maximum entropy principle. And it says that a system tends to maximize the entropy subject to macroscopic constraints. And in particular, if our system is governed by a time-independent Hamiltonian, we know that the entropy is the energy is a conserved quantity, so that it is a constraint. And if we just maximize the entropy subject to the energy constraint, then mathematically we know that we get a thermal state. In this sense, thermal state just a maximum entropy state subject to at a particular energy. And the reason that we expect the maximum entropy principle is there are some reasons. For instance, if suppose that our system is chaotic, then one might expect that chaotic dynamics just tends to increase your entropy, so that you have maximum entropy principle from chaotic dynamics. A different way of looking at the situation is that in some cases, we might assume that the so-called typicality, that is, if we consider, because energy is a constraint, and if we consider all states subject to the constraint, then these states form a set or form a space, then one might expect that a random state in this set it represents your physical system. And if that is true, then we know that random states almost has a maximum entropy. So this is another reason that's why we expect the maximum entropy principle. And in order to give a more mathematically precise discussion, I need to introduce a definition of the entropy thermalization. And there are some words, and I will go through it slowly. And as I said, we consider isolated quantum many-body systems, and it is divided into subsystem A and its complement. And we say that the entropy of subsystem A thermalizes if, after a long time evolution, it is to leading order equal to the thermodynamic entropy of A at the same energy. First, I would like to say that entropy is usually referred to as extensive quantity, that is proportional to the system size. Here we consider subsystem, so that it is proportional to subsystem size. So to leading order, it is just a linear in size of A. So to leading order equal to means that if we define so-called entropy density, then the entropy density of the time-evolved state is equal to the entropy density of the thermal entropy. So this is the definition of entropy thermalization. And in particular, we do not assume that the size of A is small. This is because when we talk about the density, we we need the size of A to be not very small. And the conjecture here is that if we have a quantum chaos, that is, the dynamics is chaotic, then we have entropy thermalization. So I need to emphasize that this conjecture is not yet mathematically precise because we have not defined quantum chaos, and this is a tricky issue, and we will not try to define it. So this slide is mostly to give some big picture, and the contents in this slide. Not all contents in this slide is mathematically precise, but we will rely on this accurate definition later in this talk. So as I mentioned, we have defined the entropy thermalization. This is more like a concept in statistical mechanics, but we can also interpret this concept from the language of quantum information theory. That is, if we have a pure state and we can define the so-called entanglement entropy. This is just the phono-Riemann entropy of the reduced density matrix. In this sense, the entanglement entropy of the system is same as the subsystem entropy. So that previously we had defined entropy thermalization with respect to a subsystem. We can equivalently view it as a statement of entanglement thermalization. So that these two concepts are the same if the total system in the pure state. Since in this talk, we will always focus on the case that the total system is in a pure state. These two concepts are the same, so that later in this talk, I will just use these two concepts interchangeably. Okay, so the main result of this talk is that we will give a particular model, and in this model, we will prove entropy thermalization. And before I introduce the model, I would like to give some motivation of why we are interested in giving such a model. So in condensed matter physics, we know that we are handling quantum many-body systems, and these systems are typically very complicated, so that we cannot solve it exactly. And for this reason, a lot of analytical effort in condensed matter physics, condensed matter theory that we propose, we try to design exactly solve a model so that the physics can be demonstrated in a mathematically accurate way. For instance, when we talk about phase transition, we are always discussing the transfer field Ising model. And when we talk about topological order, we always begin with the so-called toric code. In this sense, these two exactly solved models just serve as basic examples, and these are for instructive purposes for new people who would like to understand this concept. And for instance, if you just open up tutorials on these concepts, you definitely see these models. And for our case, we are interested in entropy thermalization, and we will prove entropy thermalization in a nearly integral SYK model. And this, to our knowledge, this is the only model where entropy thermalization can be rigorously proved. And we hope that this model just give you a platform where you can understand the phenomena of entropy thermalization. And next, I will just introduce a model. And our model is a nearly integral SYK model. So before introducing this model, I just introduced the most standard SYK model. So for SYK model, there are two different versions. We have real SYK and complex SYK. They correspond to, so real SYK is the SYK model for Majorana fermions. And the complex SYK is for Dirac fermions. And the SYK-Q model means that we have Q-body interaction. So this model is a random all-to-all Q-body interactions between fermions. And in particular, we will see SYK2 and SYK4. So the SYK2 model is given as follows. Here, capital N is the total number of fermionic modes in our system. And we have this particular Hamiltonian. Here, A dagger and AI dagger and AJ are creation and annihilation operators for Dirac fermions. And the coefficient is called hi sub ij, and these coefficients are just Gaussian, complex Gaussian random numbers, and I add Hermitian conjugate to make sure that SYK2 is the Hamiltonian is a Hermitian. So that this is just the Hamiltonian for SYK2. And similarly, we can define the Hamiltonian for SYK4 is a four-body interaction and with complex Gaussian coefficients. And capital N is always the total number of fermionic modes. And we know that SYK2 is an integral model because it is a free fermion model in the sense that we can do a canonical transformation on the fermionic operators so that it can be transformed to a system of free fermions. But SYK4 is a chaotic model. And from these definitions, it is easy to see that both models conserve fermion number. And our results will applies to a nearly integral SYK. So in order to define it, we first introduced two infinitesimal quantities called epsilon1 and epsilon2. And the Q is a total fermion number operator. Our model consists of three terms. First term is Q, and second term is SYK2 times epsilon1. And the third term is SYK4 times epsilon1 and epsilon2. And because each term conserves fermion number, the total Hamiltonian H also conserves the fermion number. Furthermore, it is nearly integral because if we don't look at the last term, we only have Q and SYK2 term. It is integrable because it is a free fermion model. So that after adding an infinitesimal perturbation, it is nearly integral in this sense. Okay, so our result is that we have entropy thermalization, means that the dynamic, after some time evolution, the entropy of the time evolved state is to leading order equal to the thermodynamic entropy. So that lets us first work out the thermodynamic entropy. Recall that in our model, epsilon1 and epsilon2 are infinitesimal, so that the Hamiltonian, originally the Hamiltonian is H is equal to Q plus epsilon1 SYK2 and epsilon1 epsilon2 SYK4. And because we are just computing the thermodynamic property, it is a static property, and the epsilon1 and the epsilon2 are infinitesimal, we can just throw away these two terms at the cost of infinitesimal error, which can be neglected. So that we only have to compute the thermodynamic entropy of Q. And this is very easy to do because Q is a decoupled Hamiltonian. It's just the sum of some on-site terms. And if, let's say, we have a, I'm sorry, I just missed a slide. So before I calculate the thermodynamic entropy, let me say a little bit about the initial state of our dynamics. That is, we just consider the simplest initial state you can imagine. That is, we have a product state, and total number of modes is capital N, and we have little n filled modes, and capital N minus little n vacant modes, so that the filling is little n, and the filling fraction is little n over capital N. And here, the filled dots means that these modes are filled. And it doesn't matter where we place these filled modes because our model is a SYK model. And if it is a random model, and if we just if we view that model as an ensemble of models, then this ensemble is invariant with respect to permutation of indices, so that we can just place the initially filled modes anywhere. And why we start with a product state? Because it is simple, and it is also very natural and relatively experimentally easy to implement. And furthermore, it is if we look at the subsystem entropy or entanglement entropy is 0. Recall that the thermalization of entropy means that the entropy is maximal. So that it is very natural that we start with some state whose entropy is the smallest. And with this initial state, we can compute the thermodynamic entropy of the initial state. That is, we first have an initial state, which is a state with little n fermions, and we need to match the initial state with a particular thermal state, and then compute the thermal entropy. Here match means that the energy is the same. So that here you can see that if we just view Q as our Hamiltonian, then if we have little n fermions, then the energy just Q, just n, little n. So that we can just do the calculation, and eventually what we get is that if we define the feeding fraction nu as little n over capital N, then the thermodynamic entropy density is just the binary entropy. So this is very easy to see because in some sense, if you look at, because the feeding fraction is little n, is nu, then in some sense, because Q is decoupled, then in some sense, we just each side, there is a probability of nu to be occupied and the 1 minus nu to be vacant. So that just compute that entropy. This is a binary entropy. So that we have worked out the thermodynamic entropy, and we will look at our results for the entropy of the time evolved state and compare with the thermal entropy. So in this slide is a summary of results. Here, capital L is the subsystem size, that is the size of subsystem A, and capital N is the system size. And in this slide, we focus on the situation that the subsystem size is a finite fraction of system size. That is little capital L over capital N is a constant. And our results also apply to the case that capital L is less than a finite fraction of system size. For instance, if capital L is a constant, then our results also apply, in the sense that we also have entropy thermalization, but those results is not summarized in this slide. So in this slide, in this table, and for technical simplicity, we just look at the case that capital L is a finite fraction of the system size. And here, C in different cells are different positive constants, and C may depend on capital L and N. And here, I have 3 columns and 5 rows. And let me just mention it one by one. For the columns, we have the second column and last column. They have there are conditions. The condition is for nu, the feeding fraction, and the fraction of the subsystem size versus the system size. So here, the second column, the result in the second column is for half feeding, and the case here all is a logical, all the case that the subsystem size is not half of system size, is less than half of system size, because we require that L over N is always less than or equal to 1/2. And the last column is for it is away from the half feeding, and the partition is equal bipartition. So that here O and N are logical and logical AND. So that if we combine these two conditions, we will cover all the cases, because the first condition in the last column is a knot of the first condition in the second column, and the last condition in the last column is a knot of the last condition in the second column. So originally in the second column we have some condition 1 or condition 2, and the last column we have knot of condition 1 and a knot of condition 2. So in this sense, it just covers these two columns. The results just cover all the cases. And here the row is for thermal. This is just a thermodynamic entropy, and we have calculated in the previous slide. And the result is that the density, entropy density, is a binary entropy of nu. So that the result is always actually the binary entropy of nu times L. So this row is what we have already explained. And for the upper and lower bound, this is our results. That is, we do not solve the dynamics directly. Rather, we give upper and lower bounds. As long as the upper and lower bounds they match, then this is it just gives an exact solution. And if they do not match, but only match approximately, then we have an approximate solution. And here, if you look at these results, you see that we have a leading term. which is proportional to L, which is the extensive part. And we also have some subleading terms. If you only look at the leading term, you see that in different cases, the leading term is always the same as the thermal behavior. In this sense, we have proved entropy thermalization. And the subleading terms, the behavior of subleading terms may be different in different regimes. But regardless of which regime we are in, we see that our upper bound and lower bound, they are pretty close in the sense that their difference is, in the first case, is a multiplicative, log L as a multiplicative factor. And in the second case, it is differ by a factor of root log L. So that that is in different regimes, the subleading terms, they may be different, but our lower bounds and lower and upper bounds always roughly match up to at most logarithmic factor. And I will explain what random means in the next slide. So random is related to so-called typicality, and I have mentioned it briefly earlier this talk, but let me explain it further. So typicality means that the properties of a quantum many-body system are described by a typical state subject to microscopic constraints. And in our context, with our constraint is just the Hamiltonian or the particle number. That is, if you look at our Hamiltonian is given by this. So that because these two are infinitesimal, so that Hamiltonian is roughly up to an infinitesimal error, it is just a particle number. And these are conserved quantity. So that these are just our macroscopic constraint. So that in our case, we have a constraint, then we just, typicality just says that our property can be predicted from a random state subject to the constraint. That is, our property, the property under consideration is just the entropy. So that it says that the entanglement entropy at long times is equal to the entanglement entropy of a random pure state in the subspace of little n fermions. That is, we just consider a subspace consists of all pure states with a definite number of little n fermions. And this subspace, we choose a hard random state from this subspace. And the prediction of typicality is that such a random state gives you the entanglement entropy at long times. And we can see how accurate this prediction is. And this is, so the random state, the entanglement entropy has been computed in this reference. And the result is that we have a leading term and a subleading term. And depending on different regimes, the subleading terms are different. And you can see that this match our upper and lower bounds up to at most logarithmic factor. In this sense, our results give a rigorous confirmation of the prediction of the typicality argument. That is, a typicality argument not only gives the correct leading term behavior, but also at least approximately gives the correct subleading behavior. And yeah, and we can also relate our results to the so-called page curve. Here, originally, the page curve is something that emerges from black hole physics. That is, it is given by the entanglement between a black hole and its Hawking radiation. And if you look at this picture, the horizontal axis is the T. So it is the amount of the black hole. It is proportional to the amount of a black hole that is evaporated, and it corresponds to our subsystem size. So that the page curve just have this behavior, which means that originally, initially it goes up and then goes down. And this is corresponds to the maximum entropy. That if, let's say, we have a pure state, then the maximum entropy is of this particular form. So that we have the page curve. And originally, we call it page curve because it appears originally in a paper by Page, and he shows that if we have a random state, then the entanglement entropy is almost maximal, and we observe this particular curve. And one question is that how we have a random state, because a random state, it has a very large complexity. And one way of getting it is that we have a random quantum circuit. Suppose that we have, initially we have products and let it evolve with respect to a quantum circuit. As long as the circuit depth is sufficiently large, then the entanglement entropy of the time evolved state has a H curve-like behavior. That is, the entanglement entropy is almost maximal. And in our results can be interpreted as that's the appearance of the page curve. That's the maximum entropy from the evolution of a time-independent Hamiltonian. Because entropy thermalization just means that we have that is entropy is almost maximal, or we get maximum entropy principle out of the dynamic evolution. In this sense, we establish the so-called page curve from the evolution of time-independent Hamiltonian. And another topic here is that about the relationship between quantum chaos and integrability breaking. There are a lot of interest in quantum integral models, and this is because quantum integral models allow at least partial analytical solution, or sometimes they can be solved exactly. And these are platforms where we can demonstrate physics in some analytical way or in some mathematically rigorous way. But when we try to realize integral systems in real systems, we always have some maybe small perturbations. This is because experimentally we cannot realize something to infinite precision. So that we have these perturbations, and this perturbation just breaks the integrability of your model. And this perturbation might have some singular effects, and because it makes the model non-integrable. For instance, in integral systems, in many cases, we have ballistic transport with divergent conductivity. But when we have some perturbation to make it non-integrable, then the transport might become diffusive, so that the conductivity becomes finite. So that an interesting question here is that if we consider a finite size system, how large the perturbation has to be in order to observe chaotic behavior? And this question, the answer to this question might depend on the property you consider. It could be that some properties it requires larger epsilon in order to observe the chaotic behavior, but for some other properties, epsilon doesn't have to be that large. And in this talk, we are interested in entropy thermalization, and we have an answer to that question. Recall that our Hamiltonian consists of two parts, the integral part plus some perturbation to the integral part. And for the integral part, we don't have entropy thermalization. This is because the integral part is a free fermion Hamiltonian, and our initial state is also a free fermion state. So that if we only have the integral part, then the state, the time evolved state is always a Gaussian state. And for Gaussian state, we don't have entropy thermalization. That is, for Gaussian state, we do have a volume law for the entanglement entropy, but the coefficient of the volume law is not the maximal coefficient. So we don't have entropy thermalization, but we have proved that as long as we add some arbitrarily small perturbation, then eventually infinitesimal small perturbation, then eventually at very long times, we have chaotic entropy dynamics in the sense of having entropy thermalization. And this is.
Can I ask a quick question? So maybe this is premature, but this SYK2 plus SYK4 has been used to talk about the so-called Fock space localization, right? That predates many-body localization, but that was kind of a model that people look at before.
Yeah.
So in a certain sense, it's not thermalizing. Would you comment on the relation between the result and theirs?
I think that models have on-site disorder. That is, in our case, the on-site term is Q. So that one way of looking at the localization is from the eigenstates. If let's say the onside field term has disorder, then one might expect that is, let's say if epsilon 1 and epsilon 2 they are infinitesimal and the Q has onside disorder, then you know that the eigenstates are all infinitely close to product states. So in this sense, it gives you localization. But in our case, if you look at the eigenstates, then the eigenstates is actually determined by SYK2.
Yeah, but you can always pick a basis where it's diagonalized.
Yes. But in that sense, Fock space, because the transformation from real space to Fock space is not a localized transformation. So that if you localize in Fock space, it doesn't mean that it's localized in real space.
So I guess that you know, I'm just really trying to ask, you know, in some standard, people claim that this model is not fully thermalizing.
Well, it depends on first. It depends on in what sense it is not thermalizing. So what quantity you consider.
Okay.
And, at least, as I will mention later, we can prove that in this particular model it does thermalize.
Okay.
I will
of entropy.
Not just the entropy, but also for, let's say, local observables, it also thermalizes.
Okay.
Yeah, I will mention that later.
Okay.
And for the reference you mentioned, I think my understanding is that because their Fock space is not localized. For instance, if it is localized and if you just transform a localized basis with some high random unitary, then it's no longer localized.
Well, I think the original model is really just SYK2 plus SYK4. You could diagonalize in any basis you want, but their point is that near the Fermi surface, there are modes that are not thermalizing.
How about we just put aside this question and
Sure, yeah, I mean, understand.
I would like to emphasize that our results do not depend on the microscopic details of the perturbation. That is, here my perturbation, the perturbation I add is SYK4, but it doesn't have to be SYK4. As long as it is some generic term that breaks the integrability, then our proof still goes through. So this is in summary, this slide just is consistent with the conventional wisdom that by adding some generic perturbation to an integral model, then we have some non-integral and chaotic model. And I also will comment on the relationship between the so-called eigenstate thermalization hypothesis. And before doing that, I need to introduce some definitions. Here, this table is just a definition. It says that the properties in the first row, if the properties in the first row are close to thermal for states in the first column, then we say that those concepts. In particular, we have talked about entropy thermalization. This just means that if we look at subsystem entropy, if the time evolves, if the subsystem entropy of the time evolved state is approximately equal to the subsystem entropy of the thermal state, then we have entropy thermalization. And we can also talk about thermalization, which means that the reduced density matrix of the time evolved state, if the reduced density matrix of time evolved state is approximately equal to the reduced density matrix of the thermal state, then we have thermalization. And we can also say what eigenstate thermalization. Eigenstate thermalization means that reduced density matrix of an eigenstate is approximately equal to the reduced density matrix of the thermal state at the same energy. Then this is called eigenstate thermalization. Furthermore, we can have eigenstate thermalization for entropy. That is subsystem entropy of an eigenstate is approximately equal to the subsystem entropy of a thermal state. So these are just definitions of 4 different phenomena. And the reason that people are interested in eigenstate thermalization is that it's under mild additional assumptions, ETH implies thermalization. That the people would like to have some explanations of why thermalization occurs. And let's say if you initialize your system in a product state, and then you can write it as a superposition of many eigenstates. And it is very natural to guess that if the eigenstate, the reduced density matrix is thermal, then the superposition of eigenstates, the reduced density matrix is also thermal. So this is indeed true under mild additional assumptions. And in this way, ETH eigenstate thermalization hypothesis is a very popular concept, and many people study it. And furthermore, we know that thermalization implies entropy thermalization. This is because if the reduced density matrices are closed, then the entropy is also closed by the continuity of the formal entropy. And we can find out under what conditions in our model these four different concepts are valid or not valid. Here, capital L is again subsystem size, and capital N is a system size. We use a notation x is much less than y, means that x divided by y goes to 0 in the thermodynamic limit. And if x is approximately larger than y, means that x over y is lower bounded by a constant. So that we can see when ETH occur or not occur. So ETH occurs when L is much less than root n, and doesn't occur for larger L. And for thermalization, we can prove that it occurs when L is much less than n over log n, and if L is a constant fraction of system size, it doesn't occur. So if you compare these two, you see that if you are in the regime where capital N is larger than root n but smaller than capital N over log n, then you have thermalization, but not eigenstate thermalization. So this is an example of thermalization without eigenstate thermalization. And to our knowledge, this is a new phenomenon that has not been discovered before. And here, thermalization it just means the definition in the previous slide. And one intuitive way of understanding why we have thermalization without ETH is from the Hamiltonian. We can see that our Hamiltonian is integral plus some infinitesimal perturbation. And if you look at the static property, that is the property of eigenstates, then this infinitesimal perturbation only affects the eigenstates in an infinitesimal way that can be neglected. So that the the eigenstates are just this, and the Q, because SYK2 model it has fermion number conservation Q, so that when you talk about eigenstates, Q doesn't have any effects. So that the eigenstate of SYK2, this is the integral model, so that the eigenstates are just the Gaussian states. And because it is an integral model, we don't have, it's still a base ETH, but only for sufficiently small L. However, when we talk about the dynamic property at very long times, we see that the dynamic property is eventually determined by SYK4, because without this term, we don't have entropy thermalization, but with this term, we have entropy thermalization. So in this sense, the dynamic part, it is at sufficiently long times, it is reflects a chaotic model, but the eigenstates, it is reflects an integral model. This is why we have thermalization without eigenstate thermalization. And similarly, we can find the regimes when we have ETH for entropy and entropy thermalization. Our result shows that entropy thermalization occurs as long as the subsystem size is less than or equal to half the system size. But if you look at for individual eigenstates, then we have ETH for entropy only when capital L is a vanishing fraction of the system size. So that we also have a regime where we have entropy thermalization, but not the ETH for entropy. finally, let me comment on some experiments. So up to the previous slide, everything is analytical. And indeed, the phenomena discussed in this talk has already been realized experimentally many years ago. This is a paper in 2016, and it observes entanglement thermalization in isolated quantum many-body system. So the motivation here is that the maximum entropy principle gives you this thermal equilibrium, and the initial state is a pure state, and it has static zero entropy. And the experimental result is that the entanglement entropy is equal to the thermal entropy. And their model is a bosonic model, not a fermionic model, but their model also has some hopping term and the interaction terms. In that sense, it has some similarity with our model. And for their results is consistent with the so-called ETH eigenstate thermalization hypothesis. But in our model, we also observe that in some regimes, we have thermalization without eigenstate thermalization. So let me give a final summary of the content of this talk. So this talk the main result is that we prove entropy thermalization for a nearly integral SYK model, and this proof this proof only relies on the axioms of quantum mechanics and do not rely on any additional assumptions and do not use passive integral formulas, and it is completely rigorous. And to our knowledge, this is the first proof of entropy thermalization in a particular quantum system. And entropy thermalization can be intuitively understood from the maximum entropy principle. And this is so the entropy thermalization is in some sense widely expected to be true. So in this sense, we just prove something which is widely expected to be true. But furthermore, because we have a model from which we can, in some sense, solve it rigorously, we also identify a regime where we have thermalization without eigenstate thermalization. So this is a new phenomena which is not known in the previous literature. Okay, so is there any questions?
Okay, let's thank the speaker first. And yeah, questions?
Yes, I want to ask, yes, several small quantities, so the epsilons, then also 1 over n or L over n of these kind of things. So what's the order of limits?
I cannot hear you very clearly, so I don't know why.
Yeah,
Let's
say so you have several small quantities, for instance, the epsilons, but also 1 over n and L over n, these kind of things. What is the correct order of limits you have to take? Is that essential?
Okay. So here we require that time is very large, because if, let's say, t is not very large, then you can always neglect this small terms. Here we require that t is large such that the last term, the effect of last term is non-negligible. For instance, if t is larger than 1 over the product of epsilon 1 and epsilon 2, then you cannot neglect the last term in your dynamics. And that is we require that time is very large. And for epsilon 1, epsilon 2, here I choose it to be infinitesimal, but it doesn't have to be. As long as I think, as long as epsilon 1 as long as epsilon 1 goes to 0, I don't remember very clearly. For epsilon 2, it must be at least exponentially small in the system size in order our proof to be valid. And for epsilon 1, it doesn't have to be exponentially small, but it still needs to be small in some sense with respect to system size. Yeah. So that is we don't have to choose a order of limits, but the way I choose is that we specify the relationship with respect to system size. We always take the system size to go to infinity, And at the same time, epsilon2 needs to be a sufficiently small exponentially small in the system size. Epsilon1 needs to be, in some sense, small. Don't have to be exponentially small. In some sense, small in the system size. And the t needs to be much larger than any other scale in your system.
Okay, so just to confirm, it's the same question, but if I just have epsilon1, then maybe the level spacing is about 1/n or something. That's the Wigner-Dyson statistics, right? And then I could make epsilon2 like, I don't know, e to the minus e to the n. Let's say it's just super small. Am I not going to recover the integrable limit, however long time you want to evolve it?
That is, the time needs to evolve is larger than at least 1/epsilon2. So that's because the time evolution operator E is E2 minus IHT. So that's eventually we have T times epsilon1 times epsilon2 times SYK4. So that's as long as T times epsilon1 and epsilon2 is in some sense an order 1 quantity, then this cannot be neglected.
I see. Okay.
Of course, one do expect that for larger epsilon1, epsilon2, we still have, for instance, of course, one expects that, let's say, as I mentioned that for our proofs to be valid, epsilon2 must be very small. But for larger epsilon2, one still expects that we have entropy thermalization. But the weakness here is that our proof rely on the fact that epsilon2 is very small. Yeah.
Can I ask a question? Another question. So with ETH, a nice thing, I guess, is that the thermalization happens for almost all initial states, right? And so it seems that, so for you, especially in this regime where there is no ETH, but you still see thermalization, it seems that you proved it for a particular initial state, which is this matrix, which is this product state. So for other states, would you still expect this regime where there's no ETH, but there's still thermalization, or can you comment on what do you think is happening in other states?
Okay, so I will answer it in two steps. The first step is that I need to mention that all results in this work are probabilistic. That is, when I say something, it means that something occurs with high probability. And in particular, we say that ETH occur and doesn't occur means that it occurs for almost all eigenstates. And when we say it doesn't occur, then it means that almost all states violate ETH. And the same is true here for thermalization occur or not occur. And for the initial state, as I mentioned, I choose the initial state to be a particular state, but as long as the initial state is a product state, gives the same result. This is because in our model, we have a SYK model, so that this model is invariant with respect to the permutation of indices.
So that for other states, what if it's not a product state?
Okay, yeah. For other states, I expect, let's say, we could consider some states obtained from product states with some low depth quantum circuit. In such cases, I still expect that the results are true for those states. Yeah, but I didn't try to prove that in our paper. That is, our proof doesn't rely heavily on the fact that we have the initial state is a product state.
Other questions? Okay, if not, let's thank our speaker. Again. Okay, yeah, thanks, Yichen.